All right, let's start out with Lesson 7, Lewis dot structures. What exactly is a Lewis dot structure, or a Lewis structure in general? All right. So a man named Gilbert Lewis, an American chemist many years ago, developed a system in order to be able to show how elements are connected together in a covalent bond. And this has become known as Lewis dot structures, which are named after Gilbert Lewis. So for instance, we got a couple of molecules here. Water, for instance, has a chemical formula of H2O. Now we know that the chemical formula shows us the ratio between the atoms in the molecule. For instance, in this case, we have a 2-to-1 ratio. But what it does not show us is how these atoms are connected together to form a covalent bond. And remember that the whole purpose of forming covalent bonds between these atoms is to have complete full shells. So how do we know if that occurs or not? Well, the Lewis dot structure will help us with that. So simply, a Lewis dot structure is going to use dots to represent the valence electrons that are around each particular atom, and including the electrons that are being bonded between atoms. So if you see a pair of electrons like you do here with water, those pairs of electrons that are between two different atoms are covalent bonds, or representing a covalent bond. Remember that a covalent bond is represented by two electrons being shared between the two atoms, which is represented by the two dots here. All right. Now these covalent bonds are also sometimes referred as to bonding electrons. Okay, bonding electrons or covalent bonds. All right. Now we have some other dots here that are not part of covalent bonds, like these ones here. And those are known as lone pairs of electrons. Lone pairs of electrons are electrons that are paired up, but they are not bonded to any atom, all right? Or they're not forming a covalent bond between two atoms. They are valence electrons, though, and so they are important to include in your Lewis dot structure, all right, as you'll see in a moment. So lone pairs are often called non-bonding electrons, because obviously they're not forming a bond. Now, in the case of water, again, the purpose of forming covalent bonds is to help each of the atoms in the molecule attain a full, complete valence shell, or an octet of 8 electrons in that shell. So the question is that the case here? Well, let's look at oxygen, our central atom here. Does it have 8 valence electrons? Let's count. 2, 4, 6, and 8. Indeed, oxygen has 8 electrons in its valence shell, and therefore it has a full shell and is happy. Okay? So oxygen is taken care of. What about the hydrogen? Well, remember that hydrogen really does not need an octet. It doesn't need 8. It only needs 2 electrons, much like helium. So in this case, as long as hydrogen has 2 valence electrons, then it's good to go. And indeed, it does, each one of them, in fact. And that is only done because we're forming a covalent bond between the hydrogen and the oxygen that allows for that sharing of those 2 electrons to have the full valence shell. So water looks good. And so this representation of water is the Lewis dot structure for water, and shows that the 2 hydrogens are connected to an oxygen, oxygen being the central atom, and it shows you that it has a couple of lone pairs and a couple of bonding pairs, or a couple of covalent bonds. All right, so let's turn our attention to the next molecule that's represented over here, and that is CCl2O. Again, it shows us the ratio of atoms of 1 carbon to 2 chlorines to 1 oxygen, but it does not show us how they're connected together and it doesn't show us if they have complete full valence shells or not. So again, we're going to write the Lewis dot structure for this. And to do that, we put carbon in the center as our central atom, and then we bond all the other atoms, oxygen and the 2 chlorines, around that central atom, which is very typical of writing a Lewis dot structure, is having a central atom and the remaining atoms surrounding it. All right. So let's look at the bonding going on here. Covalent bonding. We have a covalent bond between each of the chlorines and a carbon. All right, as represented by there. But we also have 2 covalent bonds between the carbon and the oxygen. And when we have 2 covalent bonds between 2 different atoms, it is known as a double bond. Now we can also have a triple bond, and that would be actually 6 dots, or 3 covalent bonds that would be connected between those 2 atoms. So we can have single, double, and triple covalent bonds between atoms in Lewis dot structures that are allowed. All right. And of course, we also have lone pairs of electrons that are represented here, like a lone pair there and a lone pair there. And then the chlorines also have some lone pairs. The carbon doesn't have any lone pairs represented here. All right. So once the Lewis dot structure is made, we need to make sure that each atom is happy with having full, complete valence shells. And so let's do that. Let's start with the carbon first. The carbon has how many electrons or valence electrons around it? It has 2, 4, and then these 4 make 8. So carbon looks good, mainly due to that double bond and those 2 single covalent bonds. The chlorine has a 2 electrons from the covalent bond, and then it has these lone pairs, which make a total of 8 valence electrons. And we can see that from the other chlorine too, and it has 8 valence electrons as well. And so each of the chlorines are quite happy with their full valence shells. Now the oxygen, let's see, it has 4 electrons from that double bond, plus 2 lone pairs, which makes it a total of 8 valence electrons, and then we have a full shell. So each atom in this molecule has complete full shells, and we've have everything worked out here correctly. All right. So exactly how do we draw or make Lewis dot structures? I have come up with 6 simple rules, and if you follow these rules each time, you shouldn't go wrong. You should be able to work out the Lewis dot structures. So let's run through these rules really quickly, okay? So pay attention. You're going to have to learn these. You're going to have to memorize them. I know it's not fun, but you're going to do it anyway. And just by simply drawing Lewis dot structures, you'll begin to memorize these. Okay. So rule number 1 says count the total number of valence electrons for each atom in the molecule. All right. Simple as that. That's the first thing you always do, is count out the total valence electron number. Then step 2 is you're going to determine the central atom of the molecule. Now essentially, the central atom is the one that usually needs the most electrons to fill the valence shell. So you look at your molecule, you look at the atoms involved, and you determine which one needs the most electrons, and you place that in the center. And then you're going to put all the other atoms around that central atom. Now, if you do have a case where you have 2 atoms that need the same number of electrons, and so you can't decide, okay, which one goes in the center, then by rule of thumb, this is what I suggest you do. Always put the atom that is least electronegative, okay, the least electronegative atom in the center, and then you should be okay. All right, so you might want to add that into your rules there. Okay, rule number 3. Oops. Go back. Rule number 3 is you're going to make a covalent bond between the central atom and the other atoms in the molecule by creating a bonding pair of electrons represented by the two dots. So this is where you're going to start making covalent bonds, and you're going to use two dots between the atoms on the outside in the central atom to make those covalent bonds. Now, rule number 4 is what you're going to do is take and subtract 2 electrons from each single covalent bond drawn in step 3 from the total number of valence electrons calculated in step 1. All right? And then once you have that done, then step 5 says you're going to distribute the remaining electrons as lone pairs around the atoms. And what's important is A and B. All right? So 5A, you need to start from the outside atoms and work inward. Always start making lone pairs on the outside atoms, and then you'll go to the central atom at the end. Right? And then B, you're going to attempt to make sure that an octet or duet, now duet is just those elements that need 2 electrons only to fill their valence shell versus the octet on each of the atom. Now, if you find that an atom, this goes to rule number 6, if an atom is deficient, it doesn't have enough electrons, right, then you might need to convert a lone pair of electrons from a neighboring atom into forming another bonding pair to create a triple or a double bond. Okay? And so what we're going to do is we're going to go through these rules using some molecules and make some representations on this. So keep your rules out closely as we run through some of those. I would also suggest you use a periodic table as well to help you as we go through some of these examples here. All right? So I'm going to go to a whiteboard. All right. So we're going to go back to water, H2O. Now we've already seen the Lewis dot structure, but can we use the rules that we just went through to actually determine the Lewis dot structure? Okay? So rule number 1 states simply this. We need to count up the total number of valence electrons. So oxygen has 1, 2, 3, 4, 5, 6, if you use the periodic table, 6 valence electrons, and each hydrogen has 1. So if we count 2 for hydrogen and 6 for oxygen, that gives us a valence electron number of 10. Now, at this point, it's important to point out that the total valence electron number should be an even number. If it is an odd number, then you cannot make a Lewis dot structure of that molecule. You can only make a Lewis dot structure if you have an even number of total valence electrons. Okay? Now, step number 2 states we need to find a central atom. So you have hydrogen or oxygen. Which one needs the most valence electrons? Would be oxygen, so it's going to be my central atom. Then next, step 3, is that we're going to start forming forming covalent bonds between the central atom and the remaining atoms. So we're going to form a couple of electrons form there and a couple of electrons here. And we've made 2 covalent bonds. All right? So we've used up 4 valence electrons out of our total amount. So step 4 says we're going to take those 4 electrons, take our 4 electrons, and we're going to subtract it from our total to give us 6 electrons remaining. Actually, I miscounted this. I don't even know what I was thinking. This should only be 8. All right? Sorry, we have a total of 8 valence electrons. I can't count for obvious reasons. I don't know. But so we're going to take 8 and we're going to subtract 4 from that, and that gives us 4 electrons remaining. So step 4 tells us that we're going to take those remaining 4 electrons and we're going to distribute them. as lone pairs. So we start out with the outside atoms first. Those would be our hydrogens. And we see if we need to actually create lone pairs. And the answer is no, we don't, because hydrogen already has 2 valence electrons, each one of them, with that bond, these 2 bonding electrons. Therefore, hydrogen doesn't need any more valence electrons. Okay? So I'm going to erase this. Start all over again really quickly. Okay, so we have our oxygen, and we have our covalent bond with that hydrogen, and covalent bond with that hydrogen. Okay, now we're going to take these, since the hydrogens are okay, we're going to distribute the remaining 4 electrons as lone pairs around the oxygen. So there's 2 and another 2, and that gives us 4 minus 4 is 0 valence electrons used or left. And we have to use all of these 8 electrons. We always have to use our total amount. We should have any leftovers when we're all said and done. Okay? So now the question is, do we have a complete full octet around each of the atoms? And we do. We have 2 for each of the hydrogens. And then for oxygen, we also have the 2, 2, 2, and 2 with those lone pairs, and we have 8. And so oxygen is all good. All right. Now, one thing we can do to clean this up a little bit is that for bonding pairs, we can always substitute the 2 bonding pairs for a line, and those lines will represent the 2 dots or the 2 electrons being shared. And then we have our lone pairs. So that's something you can also do to clean up the structure a little bit. All right, so there's our example of hydrogen, or of water. All right, so let's think about another one and do another structure really quick. Let's do something like a little bit more complex. Let's do NH3. Okay? So, the first step is to determine the total number of valence electrons. So, the nitrogen has 5, and each of the hydrogen has 3. So that gives us another 8 total valence electrons. Notice I got this right this time. So, 8 total valence electrons. Number 2, what's our central atom? Well, nitrogen is, because it needs the most electrons, so that goes in the center. So now I'm going to form our bonding pairs of our hydrogens around our central atom. All right, and that's used up how many valence electrons? 6, right? So we're going to take our 8 minus 6, and that's going to give us 2 electrons remaining. So now I have 2 electrons that I can make lone pairs. So again, we're going to start with our outside atoms first. So we'll start out with the hydrogens. Well, each of the hydrogens don't need lone pairs because they all have 2 valence electrons already with those covalent bonds. So they're fine. So it's just the nitrogen. We're going to place those 2 on nitrogen as lone pairs. And that's going to use up all of our valence electrons. Now, is everyone happy? The 3 nitrogens are happy. They have 2. This hydrogen has 2, and this hydrogen has 2. The nitrogen also has 2, 4, 6, and 8 around it. And so the nitrogen is also happy and have a full valence shell. All right? Let's do one more example here. Erase all of this. All right. Our last example is going to be with carbon dioxide. Okay. Carbon dioxide has the chemical formula CO2. All right. So let's count up the total valence electrons for carbon dioxide. The oxygen, each one of those has 6 valence electrons. So we would have a total of 12 valence electrons for the oxygens, and then The carbon has 4 valence electrons, so that gives us a total of 16 valence electrons. All right. Now, what atom goes in the center? Carbon or the oxygen? Carbon does. Why? Because it needs more electrons than oxygen does to have a full valence shell. So carbon's in our center. Then we're going to go ahead and put oxygen. Okay? And we'll form our covalent bonds with the oxygen. That uses up 4 electrons. Okay? And that leaves us with 10. Or 12 valence electrons left over. Alright, so what do we do with these 12 valence electrons? That's right, we're going to distribute them around the atoms as lone pairs. Now we're going to start out with the outside atoms first and then go to our central atom. So the oxygens are the outside atoms. So we're going to add 2, 4, 6, okay? No more for oxygen. Another 2, 4, and 6. And that's no more for oxygen. And that actually used up our remaining 12 electrons. So we have 0 left. Okay? We have no more electrons that we can distribute around. Alright, so now we got to see if everyone has a complete octet or not. Okay? So let's start counting. Oxygen has 2, 4, 6, 8. Oxygen's great. This one, 2, 4, 6, 8. That oxygen is great. So all the oxygens are great. So let's see about the carbon though. Carbon has 2, 4. Carbon's missing 4 electrons. Carbon is in problems here. Alright, it does not have enough electrons to complete its valence shell. And there's no more to take or to use. We've used up all the possible valence electrons. So what can we do? Well, this goes to the last rule, number 6. What does this say? It says that if we're deficient in valence electrons, then we need to take or borrow a lone pair of electrons and make a double bond. And so that's exactly what we're going to do. So let me clean this up again, really clean this up so we can kind of see here. So we have our carbon, we have our oxygen, and then we have our lone pairs. Okay, so what I'm going to do is I'm going to steal a lone pair from this oxygen, and I'm going to make another bond between that carbon. That creates a double bond. Alright? And then I'm going to do the same thing with the other one because carbon, remember, is still deficient in 2 more electrons. So I'm going to steal or borrow a couple of lone pairs and create another covalent bond. Now, did this destroy anything about oxygen? No, it didn't. Because if you look at it, oxygen still has 2, 4, 6, and 8 electrons around each one of them. It's just now, instead of a lone pair, it's now another covalent bond to form a double bond, okay? And then the carbons are great because they have 4, and 4 makes 8 valence electrons with that double bond. So simply, if we were to make this all look nice and pretty and organized, we could simply say we have a carbon with a double bond, oxygen, and another double bond oxygen, and each of the oxygens now only have 2 lone pairs around each of those oxygens, okay? And that makes everyone happy and content, okay? So that's simply how we draw Lewis dot structures. We'll practice some more of this in class and for homework, but this is it right now for this particular lecture video.